When we dealt with sequences, we were not only interested in finding any term of the sequence but also in finding the sum of the sequence. Through determining the general characteristics of the sequences, the sum of any number of terms can be solved for all n which are elements of the set of natural numbers. The proof that the formula is applicable for all n in this set is done using mathematical induction. The principle of mathematical induction, or PMI, is a way of establishing that a given statement, usually in the form of equations and inequalities, holds for any natural number. This principle is analogous to the principle of domino effect. That is, dominoes are aligned and erected so that when the first one falls, the next domino will follow to fall, and so on. There are three parts of mathematical induction. The first part aims to prove that the given statement holds for n equals 1, 2, 3, and so on. The second part is the hypothesis of induction. Assume that the same statement is true for any counting numbers k. Then, we're gonna prove that if the given statement holds for some natural number k, then the statement is also true for the succeeding natural numbers k plus 1. Then the last part, or the last step, is the conclusion. Let us have some examples. Number 1. Prove that the sum of the first n counting numbers 1 plus 2 plus 3 plus and so on plus n is equal to n times the quantity n plus 1 over 2. So we follow the three steps. First is the verification part. To prove that 1 plus 2 plus 3 plus and so on plus n is equal to n times the quantity n plus 1 over 2 means to test whether the statement is true for all positive integral values of n. For the statement to be true, it must be true for n equals 1, the smallest element of the set of positive integers. If n is equal to 1, the statement becomes 1 equals 1 times the quantity 1 plus 1 over 2. Ang unang term sa left side ay 1. It must be equal to the right side. We just replace n with 1. If we simplify, the value is equal to 1. 1 plus 1 is 2, times 1 is 2. Divide by 2 is 1. Thus, the statement is true for n equals 1. How about when n is equal to 2? We have here 1 plus 2 since we have two terms on the left side, and it should be equal to the value on the right side if we replace n by 2. Simplify, 1 plus 2 is 3, and 2 plus 1 is 3 times 2 is 6, divide by 2 is equal to 3. Thus, the statement is also true for n equals 2. How about when n is equal to 3? On the left side, we have 1 plus 2 plus 3, since these are the terms on the left side. Then on the right side, we replace n with 3. Simplify, we have 1 plus 2 plus 3, which is equal to 6. And 3 plus 1 is 4, times 3 is 12, divide by 2, that is equal to 6. So we have verified that the statement is true for n equals 1, 2, 3, and so on. You can try or solve for more values. However, showing that the statement is true for n equals 1, 2, 3, or any larger value of n does not completely prove the statement. So we proceed to the second step. We assume that the statement is true for value of n, say n equals k. We have 1 plus 2 plus 3 plus and so on plus k equals k times the quantity k plus 1 over 2. We just replace n by the variable k. And this is what we called the inductive hypothesis. Now, does it hold for the next integer, which is n equals k plus 1? Here comes the challenge. We're gonna prove that 1 plus 2 plus 3 plus and so on plus k plus 1 is equal to the quantity k plus 1 times the quantity k plus 1 plus 1 all over 2. From our inductive hypothesis, we just add k plus 1 on the left side since we're gonna see if it holds for n equals k plus 1. And on the right side, we replace k by k plus 1. So here's our proof. On the left side, we copy these values. And on the right side, we have k times the quantity k plus 1 over 2 plus k plus 1. Here's our technique. In proving, we start with our inductive hypothesis. And we just add k plus 1 to both sides since we're gonna prove if it holds for n equals k plus 1. Next, we take the sum of the fraction. Find the LCD, and that is 2. Simplify, 2 divided 2 is 1, times the numerator, k times k plus 1, is also k times the quantity k plus 1, plus 2 divided 1, this value has a denominator which is equal to 1. So 2 divided 1 is 2, times the numerator, k plus 1, is 2 times k plus 1. Then find the common factor if there's any. We have here a common factor which is equal to k plus 1. So we factor out k plus 1. Then we just copy k and plus 2. If we distribute k plus 1 to this factor, we will get back to this expression. Now to arrive at this value, we can manipulate this term. So we can write it as the quantity k plus 1 plus 1, since 1 plus 1 is equal to 2. And this expression is exactly what we want. Since we proved that the statement holds for n equals k plus 1, we therefore conclude that the numbers are true by mathematical induction. Another example. Prove that 1 cube plus 2 cube plus 3 cube plus and so on plus n cube is equal to n squared times the quantity n plus 1 squared over 4. First, we verify if the statement is true for all positive values of n. If n is equal to 1, we have 1 cube equals 1 squared times the quantity 1 plus 1 squared all over 4. We replace n by 1. Simplify, 1 raised to 3 is 1. 1 plus 1 is 2, and 2 squared is 4, times 1 squared, which is 1, so 4 times 1 is 4. Divide by 4 is equal to 1. When n is equal to 2, we have 1 cube plus 2 cube equals 2 squared times the quantity 2 plus 1 squared over 4. Replace n by 2, and on the left side, we copy the first two terms. Simplify, 1 raised to 3 is 1, and 2 raised to 3 is 8, so 1 plus 8 is 9. Here, 2 plus 1 is 3, raised to 2 is 9, times 2 squared, which is 4, is 36. Divide by 4 is also equal to 9. You can try more values to verify. Next, we have our inductive hypothesis. We let n be equal to k. Then, we need to prove that the statement holds true when n is equal to k plus 1. We copy the left side of the inductive hypothesis and then add k plus 1 raised to 3. Bakit may exponent na 3? Please take note that we just replace k with k plus 1. Kaya kung may exponent dito ang k, we need to follow that form, okay? Then on the right side, we also replace k with k plus 1. Remember, our proof starts with inductive hypothesis. Then we just add k plus 1 to both sides. But take note that if k has an exponent, we must also raise k plus 1 by that exponent. Next, find the LCD, which is 4. Then simplify. 4 divided 4 is 1, times the numerator, k squared times the quantity k plus 1 squared is also k squared times the quantity k plus 1 squared, plus 4 divided 1 is 4, times k plus 1 cube is 4 times k plus 1 raised to 3. Then find the common factor. The common factor is k plus 1 squared. Take note that dito meron pa tayong isang k plus 1 na factor since we just factored out k plus 1 raised to 2. Then we copy k squared plus 4 times k plus 1. Again, meron pang isang k plus 1 na factor dito since we just factored out k plus 1 quantity squared. Then we distribute 4 to k plus 1. We have 4k plus 4. Next, we factor k squared plus 4k plus 4, and that is k plus 2 quantity squared. Finally, manipulate the term. We have quantity k plus 1 quantity squared. K plus 1 quantity squared is equivalent to k plus 2 quantity squared. 1 plus 1 is 2. And this is exactly the same expression with this. Therefore, the statement is true for all counting number n by mathematical induction.